Okay, started in black and white here anyway. Go back to the roots like our book here. Once again, very important to take a look at the book and examples of what are and are not instances of these rules of equivalence. Don't have time or space to really cover that here. There's quite a bit to these rules. These rules are, we've made a shift here, rules of equivalence. We are not working on rules of inference, which we had before. What's pictured here on both sides of the arrow in all instances here, 8 different instances. So again, we have quite a bit, and in several cases we're talking about 3 different expressions, some of which we're just talking about 2. Most of which we're just talking about 2. But these rules of equivalence are literally logically equivalent expressions. And since these expressions are logically equivalent, we could do truth tables to show that everything on the left in all cases is equivalent to what's on the right, in each individual instance, of course. They're literally the same, so we can make a substitution at any point in a proof, and that can even be true within a line. It doesn't just have to be we replace one line or claim in a proof with another, but rather a part of a line can be respecting parentheses replaced with a logically equivalent expression. So with rules of equivalence, we will always cite just one line number in our proofs. And the other point here is that they can be used or applied to a part of a claim or a line. Okay, logically equivalent expressions, in other words, can be substituted for one another at any point with the what should be obvious rider that we respect parentheses. Okay, I'm not going to do the examples really here, but let's just take a look at the rules here. Top left, commutation, abbreviated COM. This one's fairly simple, and it simply says that P or Q is equivalent to Q or P. The order of an or statement or disjunction does not matter. So if we, all right, we'll have a quick example, but if I have not A or B, I can say that's line 1 of a proof. I can then substitute that for B or not A, and that would be commutation on line 1, if you will. And to show the within part, I guess since I'm early here, I'm going to go ahead and do that. Let's say I have, I'm going to go, well, no, I'm going to stick with or. Let's say I have not A or not C, then D and E, and then I can flip the not A and the not C, either side of the or. All right, we need some parentheses here to disambiguate, but here I'm making a substitution, not just substituting, or writing an entire line as per the rule, but within it, I can just change the not A or C to not C or not A, and then keep the rest the same, and that's an instance of commutation as well. Commutation right here, D and E, is the same as E and D by rule. By our second version of commutation, it applies to both or and expressions where with both of those, the order does not matter. Also true for if and only if, but that's a different story here and fits together in the rule system in a different way. Okay, so once again, commutation says 2 things. We have an or statement, and it's got to be literally this. It's got to be one or statement grouped together in parentheses. We can flip the order with an or with an and. Exportation, somewhat complicated rule, but we only have one version of it. And with exportation, we have the expression on the left, which says if P, then if Q, then R, is logically equivalent to saying if P and Q, then R. And sort of try to talk this out, think about it. On the left, we have, if you got P, then Q will get you R. That turns out to be, and is probably intuitively equal to the same thing. If you have both P and Q, then you get R. You can do a truth table. It's only going to be one particular case where both expressions are false. Incidentally, it's where P and Q are both true, and R is false. It's going to be true in all other cases based on our definitions, and 8-row table is what it would take. Going on to association, okay, abbreviated ASSOC. This also quite intuitive, straightforward rule, but complicated in a couple senses. First of all, we have two different formulations, and secondly, we have three different expressions, P, Q, and R. And of course, P, Q, and R can stand for anything. They can themselves have any amount of logical complexity in them. If you take a look here, the top formulation says if we have P or Q grouped together or R, that's equivalent to P or Q or R. In both cases, it's going to be true when at least one of those things is true. And it's going to be false only when all three of those are false. Similarly, at the bottom here, we have P and Q grouped together, and R is logically equivalent to P and Q and R. P and both Q and R, we would put it in language and as pictured. All right, going on to De Morgan, something that came up in various ways in translation. And that hopefully has become clear as you've gone through this. We have a formal rule for this so we can incorporate it in our proofs. It's not the case that either P or Q. That is saying the same thing as P is not true and Q is not true. On a related note, if it's not the case that both P and Q, it's not the case that group together P and Q, that's just saying that P is not true or Q is not true. It could both be not true, but the left and the right here both say exactly this, not both P and Q. Finally, we have material implication, and this is, kind of revealing. We've talked about this before. It's been shown in different ways in chapters 3 and 4. But if P then Q turns out to say no more and no less than this, P is not true or Q is true. A different way of putting this: if P then Q is true, unless P is true and Q is false. So to avoid P being true and Q being false, we either need P not true or Q true, and that's the material implication rule. Okay, so there's definitely some practice to do with the rules, to think about these different formulations, look at the examples in the book, but that's an overview of our 5 rules of equivalence here in 4.4.